hold on.
Okay, so Goa campus. Okay, good morning students. So now back again, still continuing with our discussion on the frequency response. Okay, so we missed 2 classes. Possibly one day I will take a class, extra class 5 to 6. So be ready with that. I hope you all are free at 5 or 6, 5 to 6 any day. I can announce it. Now cascode amplifier, as I said, we would mainly focus on the intuitive analysis. How to estimate poles and zeros using intuitive analysis. So as I said, roughly every node leads to a pole. And then identify the feed forward path to get the expression for zero transmission. So this we were discussing last time. So we have how many nodes? Node A, node X and node Y. This R can be active load, can be passive load. Accordingly, you have to take the expression. So between A and X, now actually your signal path is from A to X to Y. Okay, so this is our main signal path. You have to keep this in mind. So anything that comes up in the main signal path is of interest to us. Okay, we need to analyze it and we need to thoroughly check it. So as I said, as we move from A to X, here is a Miller component CGD1. I will call it as a Miller component because it is existing in the signal path, though it is not directly with the A and Y. But it is coming in the main signal path, so I need to take it. I apply my Miller's theorem, separate it into 2 parts and find the pole at A and find the pole at X. Okay, and the gain that I should take should be Vx upon Va, because it is this gain which will come into picture. So it should be Vx upon Va. And then move from X to Y, identify if there are any further Miller component, but there are not so, because this is not coming. कहाँ चले गए? Is the slides available at Goa campus?
Yes, ma'am.
They are able to see the slides, not here. Fine, so I think we need to only now compute the time constant. So find out the R at that node, find out the net capacitance at that node, multiply the two together, and you will get the expression for the pole frequency. Okay, zero that will exist, it will be only because of CGD1. So I can estimate a zero because of CGD1 that comes out to be same as that of a common source amplifier. And polarities you need to check for zeros, plus and minus. For poles we don't check this. We always say it would be negative by default. Why? Why? Yeah? Same? No, I'm not saying stability. I'm saying that I do not understand or I do not look into the positivity or negativity of the pole. We say it would be negative. How can we assume by default that they would be negative? Any reason? Why we assume that they are going to be negative? They will never be positive. Why we assume that? I check for transmission zero, but I do not check for pole frequencies. Why? negative, what do we mean by that? That means,
Excuse me, ma'am.
yes, yes.
Ma'am, output is bounded. That's why system has to be stable.
How do you know output is bounded? That's what I want to know. When we say pole, no, don't go other way around. Okay? Poles are negative, so output is bounded. Do not say that because output is bounded, so poles are negative. Don't put like that. How do you know that poles are negative? The moment poles are negative, we know the output is bounded. Okay? So we should not go the other way around. So why do we know that poles are negative? How do we know? How do we know? Because your networks are consuming energy. You will get a positive pole when there is a negative resistance coming up. And the systems which we are discussing, they are LTI systems. They consume energy. Every node consumes energy. So unless there is a negative resistance coming up, you will never end up in having a positive pole. Remember that. And the circuit that we are discussing, there at every node there is a consumption of energy. Always remember that. Resistances are always a dissipating component. They are not a negative resistance. If you are getting a negative resistance effect at any node, then there is a possibility of having a positive pole. Always remember that. So our circuits which we are discussing, they are all LTI circuits, linear time invariant circuits which are dissipating energy. Even MOS is also it consumes energy. It does not have a negative resistance characteristics. MOSFET does not have a negative, like in tunnel diode we have. Okay, we do not have a negative resistance characteristics. Circuits are also linear time invariant. That is why because we know those concepts, we assume by default the poles are going to be negative. We are assuming that poles are going to be negative. Otherwise, I would have checked for positivity and the negativity of the pole. So be very careful when you make a statement. You should know the reason behind each and every statement that you make. We say poles will be negative. Why? You should know as an engineer. What should I do? There is no slide. Let me see if the documents. It's a problem of projection only. We are not getting a projection here at Pilani campus. At Goa, probably we are having.
प्रोजेक्टर कुछ प्रॉब्लम है स्लाइड में मैंने डाल दिया उसी स्क्रीन पे आ जाएगी इसी स्क्रीन पे आप इसी को यूज करना पड़ेगा
तो आप लाइए तो सही
हाँ वो डाल रहे हैं
अच्छा क्लासेस या तो मैं वहाँ पे इसके थ्रू करूँ
नहीं इसी पे
ठीक है मैं इसलिए कर लूँगी कोई बात नहीं
स्लाइड को चेंज करेगा वहाँ से अच्छा आप जैसे इनको तो दिखेंगे नहीं
किनको नहीं दिखेंगे
इनको वो वहाँ से डिस्प्ले कर रहे हैं ना
हाँ
आप बोलोगे स्लाइड चेंज तो वो चेंज कर देगा
अच्छा ठीक है
प्रोजेक्टर का बंदोबस्त कर लेगा
ठीक
प्रोजेक्टर उनका भी खराब है वो भी उस पे दिखा
तो थोड़ा सा आपको आगे आना होगा यू शुड कम टू द स्लाइड नंबर लेट मी से 27 स्लाइड नंबर 27 yeah so I think all the three poles are you able to see all of you so three poles you can see slide number 27 there are three poles omega PA, omega PX and omega PY. Okay, and then there is a omega Z. What's the problem? यहाँ भी आ गया, चलो अच्छा ठीक, कोई बात चलने दो. Okay, huh? So this is all intuitive analysis. And now we move on to the IO impedance. I think you all know that's Vx by Ix you have to do at the input node and at the output node. Kindly do this for every. So IO impedance will be my next slide, that is 28. And now we move on to 29, that is CSA with source degeneration, 29 slides. Slide number 29. Now look here. This is a little bit tricky, so I am going to discuss it. Here we have a load RD. Look very carefully into the slide. There is a MOS transistor M1 and there is a source degeneration resistance RS. And the Miller component that I am showing you is CGS. Now you may ask why this? Because we also have a Miller component CGD, which is not shown here. But CGS is also one of the Miller component. The reason is this node, that is a source node. It is actually affecting your V out. So it is in the main signal path. It is reducing your V in. Look very carefully. V in is with respect to ground here. Okay, in slide number 29, V in is with respect to ground. And remember, only V1 is going as input. Whereas the rest of the input, that is a drop across RS, is actually not going as input to the main amplifier. So actually your signal, determining the signal, RS is playing a role in determining the signal input. So it is in the main signal path that way. It is in the main signal path. So I am interested about understanding the behavior of this X node in the small signal mode. Okay, so I need to consider the effect of CGS which exists between V in and X. Clear? So here we have drawn the small signal model. Slide number 29, we have R signal, that's the source resistance or signal resistance. Then I am including CGD of M1. I am including CGS. And then there is a MOS behavior, GMV1 into RO, GMB, because of body effect. There would be a C load and there would be a RS and there would be a capacitance CS at that node. So this is the entire small signal model. How many nodes we have? We have a node at V in, we have a node at V out, and we have a node at X. So roughly I assume that there would be 3 poles minimum. And I can assume that one 0 will be through CGD and another 0 may appear through CGS. So this is my intuition says that I should have 3 poles and 2 zeros. I should have 3 poles and 2 zeros. Okay, so now we come to the calculation intuitive analysis of computing each and every pole. So first of all, at the input, slide number, this is slide number 36. No? Slide number 32. Slide number 32, intuitive analysis. Look here, I am computing all the poles and zeros intuitively. So first of all, the input node. Look at the input node. Input node, we have a resistance. R signal will be there, which is not shown, but you would be having a signal resistance. Suppose there is a cascade. What would be R signal then? I have a CSA followed by a CSA with RS. What would be R signal? Because the second stage is getting the input from the first stage. So what will be the R signal here? R out of the previous stage. Remember that. Okay? And if you are applying a AC source, then your source always has a resistance. So if your signal is coming from the previous stage, it would be the R out of the previous stage. Always remember that. So now we have omega P at the input node. So R time constant, I am finding out the time constant of each and every node. So time constant is R into C. Simple. So R will be R signal here. Okay. And what would be the total capacitance at this node? It would be a component of CGD. Look very carefully. A component of CGD, a component of CGS. Okay? So that is what I am doing. I am getting the gain from V into V out. So I am saying and a gain from V into Vx. So when you take the gain from V into Vx, it is a common drain amplifier. Clear? Input is gate, output is source, behaving like a common drain amplifier. I have to use that expression. And if you move from V into out, V out, it is a common source amplifier. So that is why I am writing in this slide that CGS now will be broken as per 1 minus A common drain. Why am I writing minus here? Because common drain gain is positive. Gain of common drain amplifier is positive. The negative will come in the expression. Okay. And for CGD, I break up by using Miller's theorem. And now I am using 1 plus A CSA. Because CSA gain is negative. So the expression value becomes positive. Understand it? Clear? So I am writing that expression. Now you need to put in the ACD, CDA and ACSA. And what would be RSIG? Plug it in this expression, you will get an intuitive expression for omega P in. Clear? Okay. Now, what is omega P out? That is, look at the output node. What is the time constant of output node? So inverse of that will be omega P out. So at this node, your net resistance will be RD parallel. What is the net R out? Calculate intuitively. It would be RD. I am writing RD, but actually it would be RD parallel GM RO RS plus RO plus RS. So out of that, we need to take the dominating value. So RD parallel GM RORS, if I assume GM RORS is a large quantity, parallel combination will yield only RD. That is why I am writing here RD, otherwise it can be other value also. Clear? So RD, a net capacitance at the node V out. So it will be all parasitics, component of CGD and CL added together. Okay. So I am writing CL. Why? I may be assuming CL much dominating over other parasitic and other components of the capacitive loading. But then you should understand that when you write more accurately, all those effects will have to be added together. All those effects will have to be added together. Fine. Then you come to the node X and find out omega Px. Find out omega Px. Again find the time constant at this node. So here we have a CGS component connected. Here we have RS. There would be a certain capacitances, parasitic capacitances appearing at this node and ground, which I am calling as, say, CS. So if you break CGS, you will get a component at the X node. And what's the value of that component? It would be CGS multiplied upon CGS upon it is equal to, means you have to change. It would be multiplication. CGS multiplied by 1 minus 1 by CDA. Not getting or not getting? It would be CGS. What is the value of this component which is appearing because of the, when you break the CGS? So CGS will be broken up according to Miller's theorem. So it would be CGS multiplied by, okay? It would be multiplied by 1 upon 1 by A common drain amplifier. So you have to now add all the time constants together. Now what is the net resistance at node X? What is the net resistance at node X? It would be Rs in parallel to 1 upon Gn. There is a up component, there is a down component. Down component is Rs. Up component will be looking from the source up. That would be 1 by Gm. So that is why 1 by Gm parallel Rs, which is this. Look very carefully. 1 by Gm parallel Rs multiplied by the total capacitive load. So total capacitive load will be Cs. If I say CDA is 1 or more than 1 or less than 1 accordingly, you have to write your CGS. CGS will be, I think there is a mistake in this. There is a mistake. It would be CGS multiplied by 1 minus 1 by A. Please make this correction. There is a mistake in this. It should be CGS multiplied by bracket 1 minus 1 by ACD. So add the two components together and then you will get your net pole at X node. So net pole at X node, third pole. Then comes a 0, 0 because of CGD. So I know the expression because of common source amplifier analysis. I already know. So I simply put it in. It would be Gm by CGD. It would be Gm by CGD. Another 0 I will get here because of this CGS. Because of this CGS. Now you can do multiple of analysis. You may assume CGS more than CS. Or you may assume CGS is less than CS. I don't know. Typically value, if I assume that only parasitics will appear at node X, then CGS will be more than CS. But then the effect at this node X will be a combination of effect coming through CGS and CS. So if I assume that CS is small, so suppose at a particular frequency where CGS path is becoming active, that is current starts flowing through CGS, at that frequency CS is still working like a open circuit. Its value is low. So at this point I will assume that CS does not exist for me. So the 0 is coming at this node because of CGS. Got it? So now the current which is adding up at node X is because of current coming from the MOS and the current coming through CGS. Both these currents will be adding up in the same polarity. So what will be the kind of 0 you will get? What will be the kind of 0 you will get? Negative. Both the zeros, both the currents are adding in the same polarity. Okay, so you will get a negative 0. So a negative 0, and in that situation you have to, what will be your expression for 0? What will be your expression for 0? It would be minus. What is the expression for 0? Can you calculate the expression for 0? Add the two currents and put it equal to 0. Add the two currents, current through CGS plus the current through MOS should be equal to 0. That is what we do. Our shortcut method. So S CGS V in minus Vs. Now when I say that current Is is going 0, so Vs voltage at the source node goes to 0. Please keep on writing. Unless you write in your notebook whatever I am saying, you will never understand. Either I write or you write. Somebody should write. So the current through CGS plus the current coming from MOS should be equal to 0. So S times CGS bracket V in minus V source plus the current through MOS. How much is the current through MOS? GM times V in minus Vs. Total must be equal to 0. So what is the S value you are getting? S means J omega. What is omega value you are getting? Is it coming out to be minus GM by CGS? Yes. So this is one case where we are saying that CGS path is becoming active earlier than CS path. Now what may happen is the other way around. Suppose your CS path becomes active earlier than CGS. That means CS is more than CGS. Then your 0 will become yes. What will be your 0? Anybody who has done it? Will you get a current through CS? You will not get, because source is grounded. Another node is also grounded. So that expression will not be valid. Please mind it. You will not get any impact. So please mind it. So something is written that does not mean it must be correct. Should apply your reasoning also. Because for putting a 0, we know Vs has to go to 0. V source has to go to 0. Clear? So CS comes between ground and ground. Huh? So now we have got an expression for zeros and poles. This is for, so can you see that I am getting a very degraded frequency response. A normal CSA has only 2 poles and 1 zero. Here we have 3 poles and 2 zeros. And the moment there is an extra pole and extra zero means extra phase degradation and extra, I won't say degradation, phase change and a magnitude change coming up. So be very careful. So we do not want too many poles and too many zeros. So now we come to differential pair. That is, this slide is 33. Slide number 33. So this is differential amplifier. If you take a fully differential topology, tell me how many poles and zeros you can estimate intuitively. Slide number 33. Differential amplifier. How many poles and zeros you feel there should be? Yes? It would be input pole will be there. Now you can take half circuits, because differentially the node P will come to AC ground, the source node, the main source node, M1, M2 coupled node. That should come to AC ground. So I can have only one arm and analyze it. Whatever is true for one arm will also be true for the other arm. Clear? So you will get one arm and then analyze it is nothing but a CSA. So whatever is true of a CSA is true here. So this differential amplifier will have 2 poles, 1 zero. And 1 zero will be positive. 1 zero will be 2 negative poles and 1 positive zero. Now, people will say, generally I find this answer, it's a 2 arms means 4 poles and 2 zeros. Is it correct? I normally find people saying that. Because there are 2 arms, so 4 poles and 2 zeros. No. Remember, it is a differential. So for every, you will have a transfer function for every output node. VO1 upon Vin. You will have a transfer function. Similarly, you will have a transfer function VO2 upon Vin. When you take the differential output, you need to subtract the 2. You need to subtract the 2. So when you take the subtraction, common things come out. And magnitudes add up. So what is that common thing? VO1, now look what is here very carefully. VO1 upon Vin will be a transfer function in itself. It will be a transfer function 1 minus 1 0 upon 1 minus second pole, 1 minus third pole. 2 poles, two factors in the denominator, 1 factor in the numerator. And gain will be half GM Vin by 2. GM RO by 2, gain will be half. We all know 1 arm. If you tap only 1 arm, the gain will be half. GM RO by 2 and then the 0 expression divide by the 2 poles expression. Can you visualize it in your mind? You can. Now, same thing you visualize for VO2 with respect to Vin. Again, it will be again GM RO by 2 and then a 0 expression divide by 2 pole expression. As I said, the 2 arms are matching. So the zeros will be same, poles will be same. What will be different? Polarity. Polarity of the gain will be different. Otherwise, gain is also the same, GMRO by 2. So when you take the difference, what will happen? When you take the difference, what will happen? This GMRO by 2 minus GMRO by 2 becomes GMRO. And other factors, they come out as a common. So it actually does not lead to 4 poles and 2 zeros. It is still 2 poles and 1 zero. Have you got this thing in your mind settled very clearly? Differential amplifier does give you 4 poles and 2 zeros. Clear? You still get only 2 poles and 1 zero. Is it clear or not? So now we move on to the, what is this? This is ACM. Yes. So differential amplifier analysis we have done. So difference mode analysis. Now you come to common mode analysis. That is the next slide. 34. Slide number 34. Common mode analysis. Again do the frequency response. Because differential amplifier operates in 2 modes of operation. So you have to find the frequency response for common mode operation also. So when it is a common mode operation, okay, you need to find out, you need to take RSS into account because now node P is not at an AC ground. Node P is not at an AC ground. Clear? So you have RD, M1, M2, again a common signal is given to both the gates and then you have an RSS. And there would be a capacitance also at the node P. Parasitic capacitances will add up at this point. Parasitic capacitances come up here. Okay? So in that, now again we assume there is no mismatch. So can you assume what kind of frequency response will this give you? The 2 output nodes can be assumed to be like a clubbed together, as if they are clubbed together. Why? Because they will give you the same value. So either you fold the structure or you take half, exact. Consider a half circuit. So what will be the half circuit composed of? What will be the half circuit composed of? It would be RD. Suppose I take a half circuit, it would be RD, M1 and half of, sorry, the twice of 2 RSS. And what about CP? Half of CP. It would be one half circuit. It would be one half circuit. Take a one half circuit. Draw it in your notebook, analyze. Draw the one half circuit. Put it in your notebook and analyze. Is the structure not same as CSA with RS? Exactly. Okay, it would be just like the same as CSA with RS. So in a common mode operation, you can use the concepts of CSA with RS. With source degeneration, you may find out the poles and zeros expressions, put in the values, get the results. Again, knowing that it is an intuitive analysis, the results are approximate. Results are approximate. Clear? So we have got an expression. So now what all I can do? What all I can do is that you can plot the frequency response for ADM and the frequency response for ACM. And then if I take the ratio ADM by ACM, what will I get? Frequency response of? Yes? CMRR. CMRR will not be constant. That value will keep on changing with frequency, because gains are changing with frequency. So the ratio will keep on changing. The ratio will keep on changing. So we will have a plot of ADM, we will have a plot of ACM, and then we will keep on getting a change. So if you go to the slide number 36, that gives you the ACM analysis frequency response, which is nothing but same as CSA with RS. Exactly similar to CSA with RS. Clear? So we have got a complete effect. Now we come to, so this is about a differential topology. Now suppose you come to single-ended output topology. Can you do the frequency response analysis of this? Differential amplifier, that is the next slide, slide number 38. Now I am taking a different configuration. Single-ended output, slide number 38. Here you have asymmetry in the load. You have current mirror acting as a load. So we have again now, we have a node V in, we have a node E. I will call this as a mirror node. Node E is called as a mirror node. And I have a node V out. I have a node V out. So actually initially, remember, for fully differential, you were having only two nodes, in and out. The moment you go to single-ended output configuration, you get three nodes. Immediately that gives you a feeling that this will have one extra pole. Immediately, because every node has a time constant. Every node has a time constant. So this will add to the number of poles. And I told you, the lesser the poles, happier we would be. Because poles means degradation in the gain. I do not want too many poles, too many zeros. I would be very happy if no pole comes up. My gain will never fall. I would be happy. But since it is not happening, I am getting poles, zeros. So let me try to have minimum poles and minimum zeros. So the ideal is that you have only one pole. No zeros. Minimum number of poles or zero, that is only one. Okay, so still we are not getting that kind of a situation. We are in common source we are getting 2 poles and 1 zeros. Here we are getting 3 poles. Where? Yes, minimum 3 poles will be there. In this situation there would be 3 poles and there would be 0 also coming up. Zeros will also come up. So this will have a degraded frequency response in comparison to fully differential topology. Just by the fact that it has more number of zeros and poles. Got it? I am not saying that zeros are positive or negative, nothing. The moment I have more number of zeros and poles, I have a feeling that frequency response will be degraded. So now you try to estimate the poles and zeros. We try to estimate the poles and zeros. Because normally your frequency, this amplifier is the first stage. Normally in any op-amp, amplifier is the first, differential pair is the first stage. So it does not have any stage previously to it. So that means our input is fed directly to it. Input is given directly to it. And remember, in an IC, the pins which are going outside the IC packaging, they go to it through a pad. So there is a huge capacitance at the input pad. Now the pin which comes out, there you apply your input signal. Remember, you must have worked with any IC. You give your input signal, AC signal. Okay, so that AC signal, your function generator is connected there. The function generator is connected to the input pin. Clear? So in that situation, what will be the omega in? What will be the omega in? R of a signal source. R coming of a signal source. Okay, so this signal source is usually, because it is not coming out from an RO of a MOS device, from signal source, function generator, they usually have a 50 ohms kind of a resistance, inside resistance. 50 ohms, 100 ohms. Have you seen the ratings on the function generator? It's usually very small. So our signal is going to be very small. As a result, if you take a pole appearing at that node, if you take a pole appearing at that node, that roughly goes at high frequency. That roughly moves to high frequency. Because R into CGS will be very high. Unless the input pad capacitance comes into picture. Unless you have an input pad capacitance coming into picture. So we do not directly allow the pad to directly connect to the differential pair. Because input pad capacitance is very large. So there is an isolation between the two nodes. You do not directly connect the two together. So that is the reason that the pole omega in is normally not shown in the textbooks. Because by default they assume that this is at a high frequency, does not affect your gain bandwidth, UGB range. It does not come within that range. No books you will not find, in many books this pole be computed. But why is this not computed? You should know the reason. But yes, if this differential pair connects to the previous differential pair, then you need to take omega in into account. But remember, if that is the situation, a previous stage is there, then the input pole of the second stage automatically becomes the output pole of the first stage. by default. Am I clear or not? The input pole of the second stage is nothing but the first stage output pole. So you only compute the output poles in a cascade, because output pole of the first is automatically the input pole of the second stage. Clear? Clear? So reason why no books show omega in calculations, because we are only interested in omega out or any other pole coming in between. Okay? Now, we look at the slide number 38. How many nodes we have? We have a node in, we have a node E, we have a node V out. First of all, the very first thing, compute omega at the output node. Omega at the output node. Compute the omega. Omega at the output node. Come to the slide number 41. First of all, immediately come to slide number 41. Here the expressions are written. In the previous two slides, how do we get? Analysis is shown. But we first of all come to this slide. So there is omega P1, which is actually the omega out. Look very carefully, omega P1 is the omega out. So because what is net R out at this node? Compute. What is net R out? M4 is a PMOS and M2 is a NMOS. So what is the net capacitance? Net resistance at output node? It would be, I am writing RON parallel ROP. Why? That means I am assuming this P node comes to AC ground. Is it valid? Is it valid? Can I write P node variations to be negligible? What is the net expression you will be getting at node P? Can you compute R out by using Vx by Ix method? And then can you justify what I am writing is correct? Because dominating term is still RON parallel ROP. Can you do the calculations, R out calculations? Please do it. Okay, bell has gone. Okay. Can you do this calculation? Because you have to convince yourself that you, even in this configuration, you can assume P node variations to be really small. But then don't just assume because I am saying. Find out Vx by Ix. At output node, short the input nodes, compute your R out, and then see if it is justified to take the net R out as RON parallel ROP. That is RO4 parallel RO2. Can you do it? I want each and every student to do this analysis to convince himself or herself. Yes, go on, students. Would you do it? Every student should do it. Otherwise, you will never be convinced on your own. You have to see that P node does come to negligible variations, which you can neglect in comparison to the other nodes. So you can assume very well that P node is behaving like a AC ground, though it is actually not. So next time, everybody should come up with his or her own derivation. Okay, thank you. Now, Goa campus students, are you able to access Nalanda?
Yes, ma'am.
No problem. All the slides are there.
Yes, ma'am.
Okay.